In an earlier video, I had said that PCA can be sometimes used to speed up the running time of a learning algorithm. In this video, I'd like to explain how to actually do that, and also say try to give some advice about how to apply PCA. Here's how you can use PCA to speed up a learning algorithm, and this supervised learning algorithm speed up is actually the most common use of that I personally make of PCA. Let's say you have a supervised learning problem. Notice it's a supervised learning problem with inputs x and labels y. And let's say that your examples xi are very high dimensional. So let's say xi are 10,000 dimensional feature vectors. One example of that would be if you were doing some computer vision problem where you have 100 by 100 images. And so if you have 100 by 100, that's 10,000 pixels. And so if xi are feature vectors that contain your 10,000 pixel intensity values, then you have 10,000 dimensional feature vectors. So with very high dimensional feature vectors like this, a learning algorithm can be slow, right? Just if you feed 10,000 dimensional feature vectors into logistic regression or a neural network or support vector machine or what have you, just because that's a lot of data, that's 10,000 numbers, it can make your learning algorithm run more slowly. Fortunately, with PCA, we'll be able to reduce the dimension of this data and so make our algorithms run more efficiently. Here's how you do that. We're going to first take our labeled training set and extract just the inputs. So we're just going to extract the x's and temporarily put aside the y's. So this will now give us an unlabeled training set. So that's x1 through xm, which are maybe there's a 10,000 dimensional data, 10,000 dimensional examples that we have. So just extract the input vectors x1 through xm. Then we're going to apply PCA, and this will give me a reduced dimension representation of the data. So instead of 10,000 dimensional feature vectors, I now have maybe 1,000 dimensional feature vectors. So that's like a 10x savings. So this gives me, if you will, a new training set. So whereas previously I might have had an example x1, y1, my first training input is now represented by z1, and so I'm going to have a new sort of training example which is z1 paired with y1, and similarly z2, y2, and so on up to zm, ym, because my training examples are now represented with this much lower dimensional representation z1, z2 up to zm. Finally, I can take this reduced dimension training set and feed it to a learning algorithm, maybe a neural network, maybe logistic regression, and I can learn a hypothesis H that takes as input these lower dimensional representations Z and tries to make predictions. And so if I were using logistic regression, for example, I would train a hypothesis that outputs 1 over 1 plus e to the negative theta transpose Z, or theta transpose Z, that takes as input one of these Z vectors and tries to make a prediction. And finally, if you have a new example, maybe a new test example X, what you do is you would take your new test example X, map it through the same mapping that was found by PCA to get you your corresponding Z, and that Z then gets fed to this hypothesis, and this hypothesis then makes a prediction on your input X. One final note, what PCA does is it defines a mapping from X to Z. And this mapping from X to Z should be defined by running PCA only on the training set. And in particular, this mapping that PCA is learning, right, this mapping, what that does is it computes a set of parameters, right? It does the feature scaling and mean normalization, and is also computing this matrix uReduce. But all of these things, like uReduce, that's like a parameter that is learned by PCA, and we should be fitting our parameters only to our training set and not to our cross-validation or test sets. And so these things, the uReduce and so on, that should be obtained by running PCA only on your training set, and then having found uReduce, or having found the parameters for feature scaling, right, the mean normalization and scaling, the scale that you divide the features by to get them onto comparable scales. But having found all those parameters on the training set, you can then apply the same mapping to other examples that may be in your cross-validation set or in your test set. Okay, but so just to summarize, when you're running PCA, run your PCA only on the training set portion of your data, not the cross-validation set or the tested portion of your data, and that defines the mapping from X to Z, and you can then apply that mapping to your cross-validation set and your test set. And by the way, in this example, I talked about reducing the data from 10,000 dimensional to 1,000 dimensional. This is actually not that unrealistic. For many problems, we can actually reduce the dimensional data, by 5x, maybe by 10x, and still retain most of the variance. And we can do this with barely affecting the performance in terms of classification accuracy, let's say, barely affecting the classification accuracy of the learning algorithm. And by working with low dimensional data, our learning algorithm can often run much, much faster. To summarize, we've so far talked about the following applications of PCA. First is the compression application, where we might do so to reduce the memory or the disk space needed to store data. And we just talked about how to use this to speed up a learning algorithm. In these applications, in order to choose K, often we'll do so according to figuring out what is the percentage of variance retained. And so is for this learning algorithm speed up application, often will retain 99% of the variance. That would be a very typical choice for how to choose K. So that's how you choose K for these compression applications. Whereas for visualization applications, well, usually we know how to plot only two-dimensional data or three-dimensional data. And so for visualization applications, we would usually choose K equals 2 or K equals 3 because we can plot only 2D and 3D data sets. So that summarizes the main applications of PCA as well as how to choose the value of K for these different applications. I should mention that there's one frequent misuse of PCA. And you sometimes hear about others doing this, hopefully not too often, but just want to mention this so that you know not to do it. And there's one bad use of PCA, which is to try to use it to prevent overfitting. Here's the reasoning. This is not a great way to use PCA, but here's the reasoning behind this method, which is, if we have xi, then maybe we'll have n features, but if we compress the data and use zi's instead, then that reduces the number of features to k, which could be much lower dimensional. And so if we have a much smaller number of features, if k is 1,000 and n is 10,000, then, well, if we have only 1,000 dimensional data, maybe we're less likely to overfit than if we were using 10,000 dimensional data with like 1,000 features. And so some people think of PCA as a way to prevent overfitting. But just to emphasize, this is a bad application of PCA, and I do not recommend doing this. And it's not that this method works badly. If you were to use this method to reduce the dimensional data to try to prevent overfitting, it might actually work okay. But this just is not a good way to address overfitting. And instead, if you're worried about overfitting, there's a much better way to address it, to use regularization instead of using PCA to reduce the dimension of your data. And the reason is, if you think about how PCA works, it does not use the labels y, right? You're just looking at your inputs xi, and you're using that to find a lower dimensional approximation to your data. So what PCA does is it throws away some information. It throws away or reduces the dimension of your data without knowing what the values of y is. So this is probably okay. Using PCA this way is probably okay if, say, 99% of the variance retained, if you're keeping most of the variance. But it might also throw away some valuable information. And it turns out that if you're retaining 99% of the variance or 95% of the variance or whatever, it turns out that just using regularization will often give you at least as good a method for preventing overfitting, and regularization will often work better, because when you're applying linear regression or logistic regression or some other method with regularization, well, this minimization problem actually knows what the values of y are, and so is less likely to throw away some valuable information, whereas PCA doesn't make use of the labels and is more likely to throw away valuable information. So just summarize, it is a good use of PCA if your main motivation is to speed up your learning algorithm, but using PCA to prevent overfitting, that's not a good use of PCA, and using regularization instead is really what many people will recommend doing instead. finally, one last misuse of PCA. So I should say PCA is a very useful algorithm. I often use it, for the compression or the visualization purposes. But what I sometimes see is also people sometimes use PCA where it shouldn't be. So here's a pretty common thing that I see, right? Which is if someone's designing a machine learning system, they may write down a plan like this. Let's design a learning system. Get a training set, and then what I'm going to do is run PCA, then train logistic regression, and then test on my test data. So often at the very start of a project, someone will just write out a project plan that says, let's do these 4 steps with PCA inside. Before writing out a project plan that incorporates PCA like this, one very good question to ask is, well, what if we were to just do the whole thing without using PCA? And often people do not consider this step before coming up with a complicated project plan and implementing PCA and so on. And so specifically, what I often advise people is, before you implement PCA, I would first suggest that do whatever it is, take whatever it is you want to do, and first consider doing it with your original raw data XI. And only if that doesn't do what you want, then implement PCA and consider using CI. So before using PCA, instead of reducing the dimension of the data, I would consider, well, let's ditch this PCA step, and I would consider, let's just train my learning algorithm on my original data. Let's just use my original raw inputs XI. And I would recommend, instead of putting PCA into the algorithm, just try doing whatever it is you're doing with the XI first. And only if you have a reason to believe that doesn't work. So only if your learning algorithm ends up running too slowly, or only if the memory requirement or the disk space requirement is too large, so you want to compress your representation. But only if using the XI doesn't work, only if you have evidence or a strong reason to believe that using the XI won't work, then implement PCA and consider using the compressed representation. Because what I do see is sometimes people start off with a project plan that incorporates PCA inside, and sometimes whatever they're doing will work just fine even without using PCA instead. So just consider that as an alternative as well before you go and spend a lot of time to implement PCA and figure out what K is and so on. So that's it for PCA. Despite these last sets of comments, PCA is an incredibly useful algorithm when you use it for the appropriate applications, and I actually use PCA pretty often, and for me, I use it mostly to speed up the running time of my learning algorithms, but I think almost just as common an application of PCA is to use it to compress data, to reduce the memory or disk space requirements, or to use it to visualize data. And PCA is one of the most commonly used and one of the most powerful unsupervised learning algorithms. And with what you've learned in these videos, I think hopefully you'll be able to implement PCA and use them to all of these purposes as well.